So let me quickly go over again what we've talked about so far, and then we'll take it forward onto something new. So initially we always started, this is my point of rotation for this little duct tape covered plasticine blob. So that's my point of rotation. Where the drawing pin is, that's the point of application of the force. That's where the force is acting. And initially we always started with problems where this force was at right angles to a line joining the point of application with the point of rotation. So it was always ending up at right angles. So this might have been a seesaw, or it might have been a wrench or something like that. But the point of rotation, draw a line to where the force is acting, the force was at right angles to that. Then what we looked at was what happens if that force is at an angle. And so we looked at that initially in terms of what that does to the lever arm. So when you rotate that force around, this line joining point of rotation to point of action of the force is no longer the lever arm. The lever arm is the shortest distance between the point of rotation and this line of action. So the lever arm would now be somewhere here. Excuse me, just find my pen. And this would be a right angle. I'm just going to do that with the mouse. It's a little bit slow with the pen. So it's going to be a bit untidy, this, my apologies. And then if the force comes further around, it's at an angle. This is not your lever arm because it's not at right angles to the line of action. The lever arm is now somewhere here. So that's now going to be the lever arm. Move it further around still. The lever arm's getting pretty small. It's going to be here somewhere. Still right angles. Sorry for the state of this drawing. Until when the lever arm is aligned, or the line of action of the force is aligned with the point of rotation, there's no lever arm at all, and therefore you've got no moment in that position. So maximum moment at right angles, because you've got the largest lever arm. We should probably just draw that on as well. So the lever arm was here. And as that force rotates around, the lever arm gets smaller and smaller. Smaller, smaller, until it disappears to zero and you get no moment at all. So that's one way of thinking about this. What we're doing in this video is there is actually another way to do this as well, and sometimes it's an easier calculation. In fact, probably usually it's an easier calculation, especially for complicated problems. So if we start with the original condition again, what we're going to do is we're going to think about what are the x and y components of this force. Now, so let's just draw on our x and y axes. So we'll take y in the usual direction, going vertically upwards. What I might do, I'm going to actually move this force back this way. So I might just take x opposite from where you'd usually take it. I'll take x in this direction. It'll just mean everything's positive. Like I say, you can adjust your x and y axes to suit the problem. You can swap them in different directions, or you can also rotate it around sometimes. It's useful. So we looked at how the moment reduced in with angle. So the moment reduced with angle because the lever arm's reducing as you move this angle round. You can get the same result if you think about the x and y components of this force. And so for a force acting in this direction, or a component acting in this direction, we have that the lever arm is equal to this distance here. It's a special case. If you join the point of rotation with the point of action of that force, so where that force is acting, we can call that D. In this special case, that is the lever arm because this is a right angle. It's the shortest distance between that point and this line of action. But if we have a component in this direction, or a force in this direction. For that direction, the lever arm is 0. It's disappeared, so that has no force whatsoever. And if we think about the x and y components of this force as it rotates, initially you've got a y component here, so Fy, and you've got 0 x component. And so f of y is large, x component is 0, and so you end up with a high moment because this f of y times this lever arm is your moment. As this starts to rotate round, that y component decreases, the x component increases. But that x component doesn't cause any moment because it's aligned with the point of rotation. The y component's reduced, so now your moment has reduced as well because that y component is reducing. And if you brought that force all the way around, it would only have an x component. The x component has no lever arm, therefore this will have 0 moment in that orientation. So we can use this as another way of figuring out for a force that's at an angle. We can use that to figure out the moment. What we can do is we can resolve this force into its x and y components and use that to get the moment. So let's do that. So we want to resolve this time. I'll do the same thing, or will I move it to a different direction? Let's say we take it around this way this time. Yeah, I think we'll take it like so. Okay. And so what we could figure out is we could determine the x and y components. So fx would be this way, and Fy would be this way. Those are the x and y components of that force. Let's draw the, imagining the nose to tail. So in this case, Fx would do nothing. Your lever arm for y, so that's the y direction here, would just be this distance. So d as we had before. And so we could just figure out Fy times the distance is equal to the moment. So moment is equal to, I'm just going to leave a space there, I'll explain why in a minute, is equal to Fy times, we'll call this the lever arm for the y component, Fy times dy. Okay, and we don't have to worry about x because x has no lever arm, therefore it's going to have no moment at all. Now, is there anything else I want to say about that? That's reasonable enough. Yes, that's what I want to say about that. Now, let's think about which way this is trying to rotate. And so that Fy component, just that Fy component, it's trying to rotate the object this way. It's pulling it that way. That's a clockwise rotation, so it's pulling it this way. It's a clockwise rotation, therefore that moment is negative. And so you again have to be careful with the sign of these moments, so that's going to be a negative value. Okay, let's try another example. What we'll do now is we'll just rotate this around. We'll get rid of all our stuff here. So in that case, the line, so in our previous case, this line joining the point of rotation with the point of application of the force was aligned with one of the axes, but that might not be the case. It might be something like this, where the line joining the point of action with the point of application with the point of rotation is no longer aligned with either of the axes, but we can still use the same method. I'm just trying to think about getting something that looks tidy. Should be okay. So imagine we've got this situation with this force. Let me just move this so it's in the middle. So what we can think about then is, again, we can take this force and decide what, or determine its x and y components. I'm just going to take x and y in their usual directions this time. So we'll call this x, this y. And so our x component of this force will be like this. Y component of the force will be like this. So you'd figure out your x and y components first, and then you'd look for the lever arms to each of those. So let me see if I can change the colour of this pen. I can. Very good. So this x component, the line of action is like so. Not very straight, I apologise. We're looking for a right angle to the point of rotation, which is here. It's at right angles. And so if we were to call this fx, and we'll call this, which one did I use? dx. This line fy, so this is f of fy, just name it. Same thing again, we find a line of action of that. So the line of action of fy is like so. Then we want to find the lever arm for that component. So we look for the line from the point of rotation at right angles to that y component, which is here. We call that dy. And then we can just add those together to get the total moment, being careful about signs. And so what have we done? We've taken our force, we've got the x and y components, then we found the lever arms to those x and y components. Then we know, and I might just minimize this just so I can write it with a pen so it looks half sensible. So then we'd have moment is equal to, and I'm going to leave spaces because I'm going to think about my positive or negative. So it'd be f of x times the lever arm for x plus fy, I'm not going to write plus just at the moment, fy times dy. So let's bring that back up again. So fy, what's it trying to do? So fy is trying to rotate, it's trying to pull it up that way. So it's rotating it this way because it's pulling up that way. So that's positive. Fx, it's also pulling it this way. It's rotating, oh sorry, fy is pulling it this way, clockwise, negative. Sorry, that's going to be negative. Fx is also going this way, which is clockwise, which is also negative. So both of those moments are negative. And so in this case, it's going to be negative f of x, negative f of y, fy. Okay, so we'll do a couple of examples of those, and then hopefully that'll become clearer as we go along. But that's the basic idea. If you're using components, just find your x and y components, then find lever arms to those x and y components. Be careful with the signs and add or subtract those moments for each component, and you'll get the overall moment. And what we found earlier, if we just delete that again, if one of those components lines up, so if one of those components lines up with the point of rotation, then you can just ignore it. So if one of those components, so in this case, the x component lines up with that point of rotation, so it's going to have zero moment, so you can ignore it. So let's try a few examples.